You've most likely had an opportunity to watch the majestic flickering lights of the night sky. Those lights are mostly stars. Our ancestors had many stories regarding those stars. Today, we know that virtually all of those stories are myths. Because through the science of astronomy, we've learned more about stars than our ancestors could even dream of.
For example, we know how old, how big, how bright, how much energy they can produce per second. We know how long they can live, and most importantly, we know that they all follow the same laws of physics as everything else. Through the gathering of data, we have learned much about the lives and characteristics of stars. Stars are born in molecular clouds, which are clouds of mostly hydrogen and helium. These clouds can be many light years across in any given direction.
These clouds are made of 78% hydrogen, 28% helium, and 2% heavier elements. When the force of gravity pulling in on the clouds surpasses the strength of the internal gas pressure pushing out, the cloud starts to form clumps. The temperature then rises within these clumps, converting particulate kinetic energy into thermal energy. All stars start off the same. However, the amount of mass it has will determine what type of star it becomes, what fusion process it goes through, and how fast it evolves. All the different types of stars fit into the H&R diagram. Within this diagram, there are three main types of stars: high mass, middle mass, and of course, low mass. The low mass process fusion is a bit different than
Hey,
high mass.
I'm gonna stop you there, big dog. We're gonna talk about high mass stars. While you're sitting and waiting, listen to my mixtape.
All right.
The high mass stars' early stages are similar to those of other stars, with an exception of a faster precession through the involved process. Unlike the cores of lower mass stars, those of high mass stars fuse elements heavier than helium in layers surrounding the core. Due to the abundance of high numbers of protons, heavy elements require incredibly high temperatures for fusion to happen. The core temperatures of stars are contingent on their masses. Thus, high masses have higher core temperatures. This is what allows high mass stars to fuse heavier elements.
High mass stars proceed to fuse increasingly heavier elements until iron. When the core is made fully of iron, the outer layers of the star expand at high velocities, leaving behind the core of what was a star. High mass stars live a very fast-paced life and die in a cataclysmic fashion. Just like other stars, high mass stars form out of cloud fragments that gravity forces to contract. Just like low mass stars, hydrogen is the first element to be fused into another. In high mass stars, however, hydrogen fusion goes through a different fusion process. Enormous fusion rates in high mass stars generate remarkable amounts of power. Many more photons stream from the photospheres of high mass stars than from the sun, and many more photons are trapped inside. The fact that there are many more photons trapped inside high mass stars than low mass stars, combined with the fact that high mass stars create photons at increasingly higher rates than low mass stars, leads to radiation pressure, a pressure caused by the abundance of photons within high mass stars. With hydrogen fusion proceeding at a fast rate via the CNO cycle, a high mass star soon begins to run low on core hydrogen fuel. The star forms a hydrogen fusion shell, and the outer layers start to expand outward, turning the star into a supergiant.
So, what is a supergiant? A supergiant is any star with a minimum mass of 10 times that of the Sun. An example is the star VY Canis Majoris. This star has a radius of 1,976,640,000,000 kilometers, or 13.2 astronomical units. In other words, the distance from its center to its surface is 13.2 times the distance between Earth and the Sun.
The fusion process that low-mass stars have is a bit different than that of high-mass stars. The fusion process doesn't fuse heavier elements because these stars never reach the needed temperatures to do so. These stars do, however, reach 50 million degrees Kelvin, which is just hot enough for hydrogen fusion. The process that hydrogen goes through in order to become helium is called the proton-to-proton chain, or the pp chain. this process consists of 3 steps. The first step consists of 2 hydrogen protons fusing together to form a nucleus that consists of 1 proton and 1 neutron. After this, the nucleus that is made from the proton and neutron fuse once again with another proton in order to make a nucleus that is made of 2 protons and 1 neutron. This pretty much sums up the second step. After that comes the third. In the third step, 2 nuclei made of 2 protons and the neutron smashed together in order to make a nucleus that is made up of 2 protons and 2 neutrons. This nucleus has now become helium and pretty much sums up the fusion process.
Let's talk about a high mass star. Within its 10,000 years of being a multiple shell fusion supergiant, the core runs out of helium and shrinks and heats until fusion of heavier elements begin. Concluding to the end of its life, the supergiant fuses many different elements in shells, and iron collects in the core. Since iron cannot provide fusion energy, degeneracy pressure accumulates fusion in the core until it can no longer support it. Then the core collapses, and in an instant the outer layers of the star expand in what is known as a supernova. Once the core collapses, it forms a sphere of neutrons, which may end up as a neutron star, which is the size of a large city, or collapse further into what is known as a black hole. Middle mass stars. An example is our Sun. The fate of our Sun is that in 5 billion years our star will lose mass, but at the same time it will expand into a red giant. This will probably engulf Mercury and Venus. 1 billion years later, nuclear fusion will come to a stop and the planetary nebula will sound the Sun as it slowly dies off and shrinks into a white dwarf. Low mass stars. As a low mass star enters its second red giant phase, helium fusion begins around the inner core after the core helium is exhausted. After 30 million years, the star then expels its outer layers in a planetary nebula, leaving behind the exposed inner core. This lasts for about 10,000 years. After the 10,000 years, all that's left of the star is a white dwarf. White dwarfs are made primarily of carbon and oxygen because the core of the low mass star never grows hot enough to produce heavier elements, and they are about the size of Earth, and to this day no white dwarf has vanished from space, so they live for quite a long time.